From the moment someone bashed a rock on the ground to make the first sharp-edged tool, to the debut of the wheel to the development of Mars rovers and the internet, several key advancements stand out as particularly revolutionary. Modern inventions tend more toward improving than transforming, an app that connects the world in a better way, planes that fly farther, faster, but there's still room, every so often, for dramatic advances like, say, 3D printing or the internet. So in this video, we're going to tell you the most important invention of the 20th century. The video is going to be amazing, so make sure you stick till the end. Before starting the video, be sure to smash that like button and subscribe to never miss out on any of our videos. You can forget inventions like air conditioning, television, the computer, and the internet. The single most important invention of the 20th century was the transistor, according to some researchers and analysts. The invention of the field effect transistor, FET, proved to be elusive for many years, with a number of people postulating ideas but not being able to make a real device. The term Mosfet, full form, is metal oxide semiconductor field effect transistor. Mosfet is one type of power transistor device mostly used in VLSI circuits, CMOS digital circuits, microprocessors, and memory devices, etc. Although the Mosfet is a 4-terminal device with source S, gate G, drain D, and body B terminals, the body or substrate of the Mosfet is often connected to the source terminal, making it a 3-terminal device like other field effect transistors. Mosfet is by far the most common transistors in both digital and analog circuits, though the bipolar junction transistor was at one time much more common. The working of a Mosfet depends upon the MOS capacitor. The MOS capacitor is the main part of Mosfet. The semiconductor surface at the below oxide layer is located between source and drain terminals. It can be inverted from P-type to N-type by applying positive or negative gate voltages. This ultra-thin insulated metal gate electrode can be thought of as one plate of a capacitor. The isolation of the controlling gate makes the input resistance of the Mosfet extremely high, way up in the megaohms region, thereby making it almost infinite. As the gate terminal is electrically isolated from the main current carrying channel between the drain and source, no current flows into the gate. And just like the JFET, the Mosfet also acts like a voltage-controlled resistor where the current flowing through the main channel between the drain and source is proportional to the input voltage. Also, like the JFET, the MOSFET's very high input resistance can easily accumulate large amounts of static charge, resulting in the MOSFET becoming easily damaged unless carefully handled or protected. MOSFETs are particularly useful in amplifiers due to their input impedance being nearly infinite, which allows the amplifier to capture almost all the incoming signals. The main advantage that is requires almost no input current to control the load current when compared with bipolar transistors. The MOSFET is classified into two types based on the type of operations, namely enhancement mode, MOSFET, E-MOSFET, and depletion mode, MOSFET, D-MOSFET. These MOSFETs are further classified based on the material used for construction as N-channel and P-channel. So in general, there are 4 different types of MOSFETs: N-channel depletion mode, P-channel depletion mode, N-channel enhancement mode, P-channel enhancement mode. The history of the field effect transistor is interesting because the first ideas for the invention of the field effect transistor surfaced in the 1920s, and when Bardeen, Brattain, and Shockley invented the point contact transistor, they had been intended to make a FET but could not get it to work. Accordingly, the invention of the field effect transistor was a major hurdle, and it took improvements in semiconductor refining as well as fabrication technologies, and in particular the development of oxide layers on silicon to enable this electronic component to be made properly. The basic principle of this kind of transistor was first patented by Julius Edgar Lilienfeld in 1925. 25 years later, when Bell Telephone attempted to patent the junction transistor, they found Lilienfeld already holding a patent worded in a way that would include all types of transistors. Bell Labs was able to work out an agreement with the Lilienfeld, who was still alive at that time. It's not known if they paid him money or not. It was at that time the Bell Labs version was given the name bipolar junction transistor or simply junction transistor, and Lilienfeld's design took the name field effect transistor. The main advantage of a MOSFET is that it requires almost no input current to control the load current when compared with bipolar transistors, bipolar junction transistors, or BJTs. In an enhancement mode MOSFET, the voltage applied to the gate terminal increases the conductivity of the device. In depletion mode transistors, the voltage applied at the gate reduces the conductivity. MOSFETs are capable of high scalability, Moore's law, and Dennard scaling, with increasingly miniaturization, and can be easily scaled down to smaller dimensions. They also consume much less power and allow higher density than bipolar transistors. The MOSFET is also cheaper and has relatively simple processing steps, resulting in a high manufacturing yield. The MOSFET is fundamental to building high-density integrated circuits, ICs, and VLSI devices since MOSFETs can be made with either P-type or N-type semiconductors. Complementary pairs of MOS transistors can be used to make switching circuits with very low power consumption. In the form of CMOS logic, the name metal oxide silicon (MOS) typically refers to a metal gate oxide insulation and silicon semiconductor. However, the metal in the name MOSFET is sometimes a misnomer because the gate material can also be a layer of polysilicon, polycrystalline silicon. Similarly, oxide in the name can also be a misnomer, as different dielectric materials can be used with the aim of obtaining strong channels with smaller applied voltages. The depletion mode MOSFET, which is less common than the enhancement mode types, is normally switched on, conducting, without the application of a gate bias voltage. That is, the channel conducts when V is equal to 0, making it a normally closed device. For the N-channel depletion MOS transistor, a negative gate source voltage, V, will deplete, hence its name, a conductive channel of its free electrons, switching the transistor off. Likewise, for a P-channel depletion MOS transistor, a positive gate source voltage plus V will deplete the channel of its free holes, turning it off. In other words, for an N-channel depletion mode MOSFET, plus V means more electrons and more current, while the minus V means fewer electrons and less current. The opposite is also true for the P-channel types, then the depletion mode MOSFET is equivalent to a normally closed switch. P-channel MOSFET. The drain and source are heavily doped P+ region and the substrate is an N-type. The current flows due to the flow of positively charged holes, also known as P-channel MOSFET. When we apply negative gate voltage, the electrons present beneath the oxide layer experience repulsive force and they're pushed downward into the substrate. The depletion region is populated by the bound positive charges, which are associated with the donor atoms. The negative gate voltage also attracts holes from the P+ source and drain region into the channel region. N-channel MOSFET. The drain and source are heavily doped N+ region and the substrate is P-type. The current flows due to the flow of negatively charged electrons, also known as N-channel MOSFET. When we apply the positive gate voltage, the holes present beneath the oxide layer experience repulsive force and the holes are pushed downwards into the bound negative charges, which are associated with the acceptor atoms. The positive gate voltage also attracts electrons from the N+ source and drain region into the channel, thus an electron-rich channel is formed. In general, the MOSFET works as a switch. The MOSFET controls the voltage and current flow between the source and drain. The working of the MOSFET depends on the MOS capacitor, which is the semiconductor surface below the oxide layers between the source and drain terminal. It can be inverted from P-type to N-type simply by applying positive or negative gate voltage respectively. The operation of MOSFET in enhancement mode is similar to the operation of the open switch. It'll start to conduct only if the positive voltage plus VGS is applied to the gate terminal and the drain current starts to flow through the device. The channel width and drain current will increase when the bias voltage increases, but if the applied bias voltage is 0 or negative, the transistor will remain in the off state itself. MOSFETs are ideal for use as electronic switches or as common source amplifiers as their power consumption is very small. Typical applications for metal oxide semiconductor field effect transistors are in microprocessors, memories, calculators, and logic CMOS gates, etc. Also, notice that a dotted or broken line within the symbol indicates a normally off enhancement type, showing that the no current can flow through the channel when 0 gate source voltage V is applied. A continuous unbroken line within the symbol indicates a normally on depletion type, showing that current can flow through the channel with 0 gate voltage. For P-channel types, the symbols are exactly the same for both types except that the arrow points outwards. The discovery of MOSFET has brought a revolution in the field of semiconductors. Let us know your opinion in the comment section below. This was all for today. Hope you liked the video. Don't forget to subscribing to Finding Tech. Stay safe and we'll be back soon with another video.